In June 8, 2020, the World Health Organization declared that about 422 million people worldwide have diabetes, the majority living in low and middle income countries, and 1.6 million deaths are directly attributed to diabetes each year. Do you know that despite all the existing solutions for diabetes monitoring and glucose level testing, such as SMPG and CPG systems, both the number of cases and the prevalence of diabetes have been steadily increasing over the past few decades? Why? Because this technology is only available for individuals who can afford the high out-of-pocket cost. Hi, my name is Wasim Durbi. I'm from Lebanon. I'm currently a senior at Notre Dame University studying civil and environmental engineering. My teammates are Gia Mancini from USA, currently a senior at George Washington University studying biomedical engineering. Noor Shidya from Lebanon, studying mechatronics engineering at Lebanese American University. Sarah Al-Arab from Lebanon, studying computer engineering at Lebanese American University. And Vanessa Lee from Japan, studying chemistry and sociology at Wellesley College. Our project mentor was engineer Anthony Yaghi. Our design was for a low-cost diabetes monitoring system. It is a non-invasive, accurate measurement of blood glucose levels with Raman spectroscopy of blood in microvessels. Don't go away, guys. This device will save millions of lives.
Blood glucose meters and test strips for self-monitoring of glucose are often inaccessible and infrequently used by people with diabetes in countries with limited resources for healthcare. Test strips can cost as much as $1.50 each, which can become quite expensive if you're testing a few times a day, almost $50 per month if you're using only one a day. Supplies for measuring blood glucose can also be scarce in health facilities, despite being needed in a myriad of clinical settings at all levels of the health system. Moreover, a serious issue that hospitals face with infectious diseases such as COVID-19 is providing proper care and monitoring to patients while protecting both the patients and the healthcare workers. One way to help accomplish this is to minimize contact between healthcare workers and patients. The intended users of our diabetes monitoring system are diabetic or pre-diabetic individuals living in low-resource settings who have limited access to clinics, cannot afford the long-term cost of testing strips, or have limited time to check glucose levels throughout the day. Clinicians will also have the ability to access the patient history and their glucose level trends stored in the device. Other important stakeholders include manufacturers, scientists, and engineers who will collaborate to come up with cost-effective solutions, technical feasibility, production, and supply chain logistics. Regulatory groups will also be an important part as they determine product safety and ensure compliance is being met. Our monitoring glucose device is designed to be accessible to low-income patients and to reduce the amount of unnecessary contact that physicians and hospitals have with patients. The device is also made to increase compliance by making it more culturally appropriate for individuals whose religious or cultural beliefs do not allow for blood to be drawn. The device will be a waterproof wristband that can continuously monitor glucose levels throughout the day, warn patients when their glucose levels are too high or too low, and store the measured data. As a result, patients will avoid the inconvenience of constantly having to measure their own blood glucose levels and will reduce the long-term costs as the system can be used over a long period of time as opposed to testing strips which can only be used once. More specifically, our design will use light spectroscopy on skin in order to determine glucose concentration. Although this technology has not yet been commercially used as a glucose monitoring system, there has been many studies indicating success and accuracy using light spectroscopy to measure glucose levels. Here's a diagram modeling how Raman light spectroscopy works. Overall, our product intends to be affordable, portable, and easy to use.
Hi, my name is Sarah, and I'll be talking about the functional architecture and specifically the code that will read the data from the patient's skin and the code that will save this data and visualize this data. And so if we enter the code, we can see first the code that reads the infrared light and sends value over to the serial. And so we have 3 integer variables, one called sensor pin, and one is the LED pin, and the third is the sensor value, which is the variable that will store this transmitted data. And so after that, we have the code that will read the sensor value, which is our variable, and it will be stored in a class called sensor. And so after that, we have the code that will read the data. And now we saw the code that sends the data over the serial, and now we have to read that data. And so in order to read that data, we have the following code that imports two classes, the serial class and the time class. And so of course we need the serial class in order to use the data that we just transmitted and save that data in a new file with using the function readline, which will give us all the data that we just read and store them as bytes. And so we'll use, of course, the class bytes in order to decode that file. And so after that, we stored those data, and now we just have to read the sensor. And so in order to read the sensor, we have that following code, which will convert our byte strings into floats numbers. And in order to visualize this data, we'll use the MATLAB library in order to visualize these data and put them in a graph. And so that's basically how we'll transmit the data from the patient and how to save these data and visualize them via MATLAB library.
Instrumentation for infrared spectroscopy includes a source, a detector, and a dispersive element, such as a prism, to allow the intensity at different wavelengths to be recorded. When lasers are used for high-precision spectroscopy, like in our case, a single detector without any dispersive elements might be sufficient. As shown in the figure, radiation passes through both a sample and a reference path. Then, the beams are directed to a diffraction device, which is the splitter, which disperses the light into component frequencies and directs each wavelength through a slit to the detector. The detector produces an electrical signal and results in a recorded response. Since we couldn't implement the block diagram of the infrared spectroscopy, we developed a simplified version of the circuit, which is shown in the following figure. In this circuit, the transmitter section includes an infrared source, which transmits continuous infrared rays to be received by a receiver module, which is the detector. The infrared output terminal of the receiver varies depending on the amount of infrared rays detected. So an operational amplifier LM358 is used as comparator circuit, which takes the place of the processor. The variable resistor R5 is used to set the sensitivity of the circuit diagram. The LED at the output is used as display to visualize the output signal of the comparator. The intensity at which the LED glows tells us about the output voltage generated from the op-amp, hence how much infrared rays were detected. When the infrared receiver does not receive a signal, the potential at the inverting input goes higher than the non-inverting input of the comparator. Thus, the output of the comparator goes low, and the LED does not glow. When the infrared receiver module receives a signal, the potential at the inverting input goes low. Thus, the output at the comparator goes high, and the LED starts glowing.
Throughout the program, we have dedicated much of our time to reading research on glucose monitoring. Our next step will be to reach out to users and experts to understand the local needs of a glucose monitoring bracelet. We would love to understand how diabetes is presented in different communities and how these individuals respond to this diagnosis as well as monitoring. We would love to interview experts to gain a deeper understanding of this technology as well as some key points to consider when providing glucose monitoring devices. In addition, we want to test our code for the potentiometer and to develop a full circuit for the bracelet. We would also want to create a CAD model to visualize the bracelet in a 3D space. We want to continue to conduct additional research on glucose monitoring and build a prototype that can be tested in our target communities.